Hey, stats kids. Today we're looking at section 7.2, hypothesis testing with the population mean is known using the normal distribution on stats with Mr. Forbes. So notes out and away we go. This one, I'm afraid, is going to be a doozy, but again, we're going to take a couple days here to go through this. So if you need more time to watch the video, you're certainly welcome to take more time. But it is going to be probably, we're going to see at the end, probably one of my longest videos of the year. So we're going to jump in. And here we go. Again, this is the big idea for statistics, one of the big things that statistics is used for, and that is hypothesis testing. So in our last video, we talked about how we kind of set up a hypothesis test. Now we're going to actually come back and make our decision. So the decision rule based on a p-value. To use a p-value to make a conclusion in a hypothesis test, we're going to compare the p-value with our alpha. And the alpha will be given to us in the problem. It could be 0.05, it could be 0.10, it could be 0.01, whatever that alpha is. Here's how we're going to run the test. If our p is less than or equal to alpha, we are rejecting the null hypothesis. And remember in the last video, we set up our null hypothesis and our alternative hypothesis. If the p is smaller than alpha, we're going to reject the null in favor of the alternative. And if p is greater than alpha, then we're going to fail to reject the null in favor of the null hypothesis. So for example, the p-value for a hypothesis test is 0.0237. What is your decision if the level of significance is for alpha 0.05? Again, we want p to be less than alpha to reject. And so when we look, we're going to see what happens. So our alpha is 0.05. Our p is 0.0237. If it helps you to compare the decimals, we're going to add the same number of place values by adding 0. So 0.02, that's definitely smaller than 0.05. So because 0.02 is smaller than 0.05, therefore we're going to reject the null hypothesis. If p-value is smaller than alpha, so yes, it is. And so we're going to reject the null hypothesis. What about an alpha of 0.01? Well, then we're asking the question, is 0.0237, is that less than 0.01? Again, we can add zeros to make the numbers look similar. There's no way that 0.02 is smaller than 0.01, so no, so we're going to fail to reject the null hypothesis. Go ahead and pause the video and try it yourself. Problem 1A and 1 and 2. All right, again, we want to see if our p is less than or equal to alpha. Here our alpha is 0.05, our p is 0.0745. Again, if you need to, you can add more decimal places by adding zeros to compare the numbers. Is 0.07 smaller than 0.05? It is not, so we're going to fail to reject the null. We're going to do the same thing with 0.0745 as our p. Is that less than 0.10? Again, we can add more zeros to look at equivalent place values. Yes, this one is. So here we are going to reject the null. Again, we're just kind of building up our steps as we work into that big complicated problem of doing a hypothesis test. Recall then, we're going to have 3 different types of hypothesis test. We're going to have a left-tailed test, and for a left-tailed test, we're going to look for the p-value in the left tail, and that's going to be a less than. For a right-tailed test, we're going to look for the p-value on a tail to the right, and that's for a greater than. And then the other option was for a two-tailed test. Two-tailed test has p-values on both tails, and that's for a not equal. Where we're going to use those. The one difference we're going to have for two-tailed test, remember these two numbers are the same, but we need to double it. So we're going to do the double of area in one tail to make that calculation a little bit easier. So again, we're going to build up. So we're going back to what we did in chapter 5. So we're using chapter 5 material here. Find the p-value for a left tail hypothesis test with a test statistic of -2.23. Decide whether to reject the null if the level of significance is alpha of 0.01. So we want to find the area under the curve. We want to find our p-value. To do that, again, I'm going to look at a little sketch, and pretty much for all of the problems, I'm going to draw a picture. And that just comes from the fact that I was a geometry teacher for so many years. And the best way to look at stuff is just to draw a picture. So our z-score of -2.23, we know is over here to the left. And we're looking at the area to the left. That's going to help us then, remember the middle is always 0. That's going to help us find our area. And to do that, we're using normal cumulative distribution function in CDF. Our left bound is our negative infinity, so negative e to the 99, comma. We're going to stop at -2.23. Our mean is 0 and 1, or 0 and 1, because they're using the standard normal distribution. We're going to type that into our calculator. That gets our p-value, which is 0.013. Now we can compare our p-value to see if it's less than or equal to alpha. Our p-value we just got was 0.013, and our alpha is 0.01. Again, we can add a decimal place there to make it look like they're the same numbers. Is 0.013 smaller than 0.10? Is 13 smaller than 10? No. So we're going to fail to reject the null hypothesis. Same thing with try yourself 2. If you want to, go ahead and pause the video, see how you do, and then come back and play the video. So here we have a test statistic z-score of -1.71. It is a left-tailed test, so we are using our left tail. So here's our -1.71. Go to the left means we want that way. Again, there's our 0. So our p-value is our normal cumulative distribution function from -e to the 99. Our upper bound stops at -1.71 with a 0 and a 1. That gets us a p-value of 0.044. Again, we're going to compare that to our alpha. So 0.044, is that less than or equal to our alpha, which is 0.05? Well, again, we can add a 0. So yes, 44 is smaller than 50. So that's true. So we are going to reject the null hypothesis. What about a two-tailed test? Find the p-value for a two-tailed hypothesis test with a test statistic of z equals 2.14. Decide whether to reject the null. The level of significance is alpha of 0.05. So now we have a two-tailed test. That means we have a positive, so right here's 0. Here's a positive 2.14. Because it's a two-tailed, that also means there has to be another number that matches, which is the -2.14 in that area as well. Now, there's a couple ways you can do this. You can find the normal cumulative distribution function of both and add them together. Or you can just take for the p-value 2 times the normal cumulative distribution function for 2.14 is our left bound to positive infinity 0, 1. And that will give us our value. So to find the area of one tail and then just double it, will get you the other p-value. And that is 0.032. And we want to compare then our p to alpha. So that's 0.032. Is that less than or equal to our alpha of 0.05? So yes, 32 is smaller than 50. So yes, we're going to reject the null hypothesis. Go ahead and pause the video and try yourself 3 and see how you do. All right, so we're going to do the same thing for a two-tailed test. So I'm going to sketch my picture for a z of 1.64. There also has to be a z of -1.64, and that's because this is a two-tailed hypothesis test. Again, there's several different ways you can find the area. You can do the left and the right and add it together, but we're just going to double, so 2 times, the normal cumulative distribution function from 1.64 to positive infinity 0, 1. And that value was 0.101. So we want to compare that with our alpha as 0.101 less than 0.1. And it's not, so we're going to fail to reject. the null hypothesis. Okay, so we're going to look then at the whole thing. The whole thing is called the z-test for the population mean. When can this be used? It can be used when the sample is random, the population is normally distributed, or for any population when n is greater than or equal to 30. That's our central limit theorem. The test statistic is the sample mean x bar, and we get our z-score from using this formula again. X bar minus mu over sigma divided by square root of n, where sigma over square root of n is our standard error. I'm going to really encourage you to put parentheses around the top and the bottom so that when you plug that in your calculator, you don't mess up order of operations. So I'm going to encourage you to use parentheses to make sure you get the right number. Pay attention to that as you're going to the video. Do try to plug in the numbers as I'm going through, pause the video, plug in numbers to make sure you're getting the same answers, to make sure you're using your calculator correctly. So we're going to go through all of the steps we need to do to look at a hypothesis test. As I go through the first couple sample problems, I'll actually number them so you can see kind of where our steps come from. And so you can follow along. You can look back and reference this as well as you're working through those problems. Number one, verify that sigma is known. The sample is random and either the population is normally distributed or n is greater than or equal to 30. So that's again checking for central limit theorem. Number two, we want to state our claim. This comes from the last video. State the claim mathematically and verbally. Identify the null and alternative hypothesis. Specify the level of significance alpha. Part four, then we want to find the standardized test statistic. Again, I'm going to encourage you to use parentheses, x minus mu over sigma divided by square root of n. Again, put those in parentheses to make sure we don't mess up order of operations. Find the area that corresponds to z. So for that, we're going to use normal cumulative distribution function. Then find the p-value for our left-tailed test, right-tailed test, or two-tailed test. Remember that comes from the type of alternative. We're using the alternative hypothesis to do that. So if the left tail, that means our H of A is, the mu is less than some number. If it's a right tail, that means our alternative hypothesis was mu is greater than some number. And for the two-tailed test, that's if the alternative hypothesis is the mean is not equal to some number. Finally, then we'll make a decision to reject or fail to reject the null hypothesis, checking our P, is it smaller than alpha? And then finally, we're going to interpret the decision in the context of the original claim. So here we go. Let's look at our next example. Hypothesis testing using p-values. In auto racing, a pit crew claims its mean pit stop time. That's, if you ever watch a race, that's when they come into the pit to get new tires and gas and stuff. They claim that their mean pit stop time for 4 new tires and fuel is less than 13 seconds. You want to have a fast pit stop time so the race car can get back out on the track. A random selection of 32 pit stop times has a sample mean of 12.9 seconds. Assume the population standard deviation is 0.19 seconds. Is there enough evidence to support the claim that alpha equals 0.01? Use a p-value. So we are using the p-value method. Later on, we're going to look at the rejection region method. This is a second way of doing a hypothesis test. And so here we go. So first we want to look at central limit theorem. That central limit theorem apply. Well, we have 32, so that's bigger than 30. So that works. So n equals 32, so we check that. Number two, then what's our claim? Well, our claim is, and they say that right here, they claim the mean pit stop time for 40 tires of fuel is less than 13 seconds. So the mu is less than 13. Because there's no equal, that's got to be the alternative hypothesis. Therefore, the null hypothesis is the mean is greater than or equal to 13 seconds. Number three, our level of significance alpha, they give that to us in the problem, is 0.01. Number four, then we want to find our z-score. Our z-score is our x bar minus mu over sigma over square root of n. That is 12.9, the sample, minus the claim, which was 13, divided by sigma, which was 0.19, divided by square root of 32. Remember, we're going to put that in parentheses to make sure we don't lose order of operations. And that gets us a z-score of negative 2.98. Okay, now we want to run our test. So we're going to look at the alternative to see what we did. So because this is going to the left, the little sign's going to the left, they want to do that because it's not equal. That means this is a left-tailed test. And so we're going to use, so here's our picture. So here's our z at negative 2.98. We want the area to the left. So we're going to do normal cumulative distribution function, negative e to the 99 to negative 2.98, 0, and 1. And when we plug that in, we get a p-value that's 0.001. So a really small p-value. And I think that was also part of number 6 as well. Number 7, then we want to check it. So is 0.001, or our p-value, is that less than alpha, or 0.01? And it sure is, because we're comparing 1 to a 10 if we add zeros to make the same place values. Therefore, we're going to reject the null hypothesis. Now is where we actually can go back and see if that's good or not. So we're rejecting the null hypothesis in favor of the alternative hypothesis. And so that's good for us because that matches the claim that the pit crew made in the problem. Now to answer this, we're going to go back to the last video. If our claim was the alternative, we're going to support or not support. So number 8, so there is enough evidence to support the claim that the mean pit stop time is less than 13 seconds. So they proved their claim. So they didn't really prove it. There's not enough evidence to reject it. So there's enough evidence to support the claim that their mean stop time is less than 13 seconds. And we're gonna just work through several examples as we go here. Next up, homeowners claim the mean speed of automobiles traveling on their street is greater than the speed limit of 35 miles per hour. Right? If you have little kids that live on the street, you don't want people speeding by because there's a chance for bad accidents to happen. A random sample of 100 automobiles has a mean speed time of 36 miles per hour. Assume the population standard deviation is 4 miles per hour. Is there enough evidence to support the claims? I'm going to start, I'm not going to number all of these, but I'll definitely talk about them. So first, does the central limit theorem apply? Yes, because there's 100, so that's bigger than 30. Next up, we want to set our claim. And our claim, they're claiming that their speed is greater than 35 miles per hour. So mean is greater 35. That's not an equal, so that's got to be the alternative. The opposite is mu is less than or equal to 35. That's the null. So remember, we're going to use the alternative to decide our test. We're testing the null, even though it's not our claim. Then we're going to find our z-score. Our z-score is x bar minus mu over sigma over square root of n. You should find all of those numbers in the problem. The mean is always the claim. So the claim of 35 is minus 35. 36 is the average, and that's the sample average, because they took a sample of 100 automotives, right? Some dad went out there with a radar gun and was like shooting cars, trying to see how fast they were going. Divided by the standard deviation, which was 4, divided by square root of 100. Again, put that in parentheses so you don't mess up order of operations. And I get a z-score of 2.5. Therefore, we want to look at our test because the alternative is going to the right. This is a right-tailed test. So we have a 2.5 to the right. There's our 0. So we're going to use our normal cumulative distribution function. Our left bound is now 2.5. We're going to positive infinity, which we call e to the 99, 0, and 1. That gives us our p-value, which is 0.006. We're going to compare that to our alpha, so 0.006 compared to 0.05. Again, we can add a decimal place to help compare the numbers. 6 is definitely smaller than 50, so we are going to reject the null hypothesis in favor of the alternative hypothesis. So that's good for the dads who are out there claiming that cars are racing by the houses too fast. And so forth, because again, our claim is the alternative, we're going to use the word support in our answer. And so there is enough evidence to support the claim that speeds on the street were greater than 35 miles per hour. Example 5, hypothesis testing using p-values. According to a study, the mean cost of bariatric weight loss surgery is $21,500. You think this information is correct? Incorrect. You randomly select 25 bariatric surgery patients and find that the average cost for their surgeries is $20,695. The population standard deviation is 2250, and the population is normally distributed. Is there enough evidence to support your claim at 0.05? So first we want to look at, because this is under 25, and so it is normally distributed, so that counts for our central limit there. So we can go ahead and do this. So here's our claim. We're claiming that the mean cost, the average cost is 21,500. So that's an equal sign, which means that is the null hypothesis. The opposite of that is it is not equal to 21,500. That's the alternative hypothesis. Therefore, we're going to do a two-tailed test because the alternative determines our type of test. Not equal is a two-tailed. We want to find our z-score. That's the average that the person took, which was 20,695 minus 21,500. Divided by the standard deviation, which is 2250, divided by square root of 25, that is negative 1.79. Technically, it's plus minus 1.79 because it's a two-tailed test. If we look at a picture for that, then we have a z-score at 1.79 to the right, the z-score at negative 1.79 to the left. We want to find that both of those areas. Again, our shortcut for that then is to do 2 times one of the areas. I'm just going to pick the positive one. So 2 times normal cumulative distribution function of 1.79 to infinity, 0, 1. And that gets us our p-value, which is 0.073. We want to compare that to our alpha. So 0.073, is that less than or equal to our alpha, which was 0.05? Well, 0.07 is not smaller than 0.05, so we're going to fail to reject the null hypothesis. That's actually good for us because that was our claim. So by failing to reject the null, which was our claim, that means we're staying with the null. And again, because our claim is the null, we're going to use the word reject instead of support when we write our answer. So our answer is going to go something like this. There is not enough evidence to reject the claim. That the mean bariatric surgery is equal to 21,500. Okay. Next. Study says that the mean time to recoup the cost of bariatric surgery is 3 years. So actually pay off the amount of surgery takes 3 years. You randomly select 25 bariatric surgery patients and find that the mean time to recoup the cost of their surgery is 3.3 years. Assume the population standard deviation is 0.05 years. And the population is normally distributed. There's our central limit theorem. Is there enough evidence to doubt the study's claim that alpha equals 0.01? So again, what is our claim? So the claim is the mean time is 3 years. So the mean is 3. And I got to get on the right notes page. And that's got to be our null hypothesis. The alternative hypothesis then is the mean is not 3, which means we're running a two-tailed test, because that's determined by our alternative hypothesis, which is not equal. That takes us to our z-score. Our z-score is then our average, which was 3.3, minus the mean of 3 divided by 0.5 over square root of 25. And again, put parentheses around that. And you should get a z-score that is 3. But because this is a two-tailed test, we actually have two z-scores. We have a positive 3 and a negative 3. We want the area to the left and the area to the right. Therefore, we're going to run our p-value. Our p-value, again, is 2 times 1 of the area under the tails. Normal cumulative distribution function of 3 e to the 99, 0, 1. And something really interesting happens here. We get a p-value of 0.03. 003, sorry. And so now we want to compare is 0.003 less than 0.01. Again, we can add another 0 to compare that. 3 is definitely smaller than 10, so we are going to reject the null hypothesis. Now, is that good for us or bad? And when I say us, I mean the claim. Is it good for the claim or bad for the claim? So we're going to reject the null in favor of the alternative, and that's not really good for the claim because that was not the claim. The alternative was not the claim. So we're rejecting the claim in favor of the alternative. And again, because our claim was the null, we're going to use the word reject in our answer. So there is enough evidence to reject our claim. That the recoup time is 3 years. And so we showed that claim is not accurate based on our information. Okay, we can also do this using a calculator. So looking at your calculator, we can use the TI-84 to make a decision to reject or fail to reject the null hypothesis at a level of significance of 0.05. Get the data from page 368, and I have that information for us. The mean was 6.2, sigma was 0.47, X bar was 6.07, N is 53. So here we're going to do this. We're going to go to stat and test. And we're doing the first one, which is a z-test. And that's actually why it's first. It's one of the most common things. We can either pull data, like we put information in a list, we could pull that data. You may have one or two of those in the homework. But for here, we're just going to use stats. And so I'm going to plug in what I know. The mean is 6.2. Sigma is 0.47. X bar is 6.07. N was 53. Then we need to decide which type of test are we doing. And I don't remember which kind of test we were doing because I did not look that up. So I need to pause for a moment as we look on page 368. All right, so we're looking on page 368. Looks like we are doing a on the wrong page. We are doing a two-tailed test. So for a two-tailed test, we want the not equal. The one that goes to the left is the left-tailed test, to the right is a right-tailed test. So we want the two-tailed test. And we're going to calculate that. You can actually draw a picture of it as well. The number we're worried about is the p-value, and that just gives us the p-value. So there's the p-value of 0.044. We want to compare that to alpha. Is that less than or equal to 0.05? Again, we can add another 0 to make the numbers look the same. Is 44 smaller than 50? It sure is. We're going to reject the null hypothesis. Repeat example 6 using a level of significance for alpha of 0.01. So we're using the same p-value, which is 0.044. Is that less than or equal to 0.01? It is not. 44 is bigger than 10. So here we fail to reject the null hypothesis. So that was one method of doing a hypothesis test that was using a p-value. Now we're going to look at our second method of doing a hypothesis test, and that is using a rejection region. It works the same, but we're going to kind of flip things. So now instead of looking at finding a p-value to see if it fits compared to alpha, now we're going to see how our z-score fits into a region. So kind of going the reverse direction, but it works kind of the same way. So here we go. A rejection region or critical region is the range of values for which the null hypothesis is not probable. If a test statistic falls in this region, the null hypothesis is rejected. The critical value Z0 separates the rejection region from the rejection region. So here's what we're going to do. We're going to specify the level of significance alpha. We're going to decide whether the test is left, right, or two-tailed, same thing we've done before. Then we're going to find the critical value Z0. If it's left-tailed, we're going to find the z-score that corresponds to an area of alpha. So for this, we're going to use inverse norm. If right-tailed, we're going to find the z-score that corresponds to an area of 1 minus alpha. If it's two-tailed, we have to use our two-tailed process for inverse norm, which was subtract it and then divide by 2 to get half. We'll sketch the normal distribution, draw a vertical line to show our z-score, and we'll see how our value compares. So here's how that works. We're looking at example 7, using rejection regions. Find a critical value for a left-tailed test. Find the critical value and rejection region for a left-tailed test with alpha of 0.01. So this is no longer our z-score. This is the area under the curve. We are so our test is left-tailed. And that tells us we're using our left-tailed picture. And that tells us our alpha is the area under the curve. So this is alpha, is 0.001. We want to find the z-score that corresponds to that alpha. To do that, we're going to say then that Z0 is equal to inverse norm of 0.01. We're going to plug that into our calculator, and that is negative 2.33. That's going to give us then our rejection region. So we want the region, the Z scale that matches that curve. Well, that goes to the left. So our rejection region has to be from negative infinity to our z-score, which was negative 2.33. So there's our rejection region. And then what we're going to do in the problem is we're going to see if our z-score fits in that region. If our z-score is in that region, we're rejecting the null. If the z-score is not in that region, then we're going to fail to reject the null. Same thing, try it yourself 7. If you want to, pause the video and find the rejection region. Again, we're going to use a left-tailed test. So left-tailed test goes that way with an alpha of 0.10. So now we have an area of 0.10 under the curve. We want to find our Z0. Our rejection region is going to go to the left. So our Z0 then is inverse norm of 0.10. That is negative 1.28. Therefore, our rejection region, because we're going to the left of that z-score, is negative infinity to negative 1.28. Again, what we would do then to run the test is we're going to find the z-score. If the z-score is in that rejection region, then we're going to reject. If it's not, we're going to fail to reject. Let's look at a rejection region for a two-tailed test with an alpha of 0.05. Well, the alpha of 0.05 is cumulative because we have two tails. So we want to find the area in two tails. So that's got to be half of the 0.05. So half of it is 0.025, which is there. The other half is here, which is 0.025. So when we find our z-score, we're going to actually have two. We're going to have a negative z0 and a positive z0. This one's going to go left to negative infinity. This one's going to go right to positive infinity. To find that value, we're going to say our Z naught is our inverse norm, 0.025. And that's going to be a plus minus 1.96. Technically, we would actually add 0.95 to that and get 0.975, and that would give us the positive value. Therefore, our rejection region has to match kind of this picture. And it's going to look like this. We're going to go from negative infinity, right? So it's going to left forever. Negative infinity, we're going to stop at negative 1.96. We're going to say union. So we're going to join these together with a union, which is a mathematical operation that just combines things. We're going to start up again at 1.96, and we're going to positive infinity. So there's our rejection region for a two-tailed test. Again, what we would do then is run our z-score and see if it matches that region. One more, try yourself 8. Go ahead and pause the video and see how you do on this one. Because we have a 0.08, we're going to divide by 2. So for our two-tailed test, we have a 0.04 here and a 0.04 here. So we're going to inverse norm 0.04. And that is going to be a plus minus 1.75. And so our rejection region is going to be negative infinity to a negative 1.75 union. So we have negative infinity this way to our negative 1.75. We're going to pick up again at 1.75 to positive infinity. Decision rule based on rejection region. To use a rejection region to conduct a hypothesis test, calculate the standardized test statistic Z. If the standardized test statistic is in the rejection region, we're going to reject it. If it's not, then we're going to fail to reject. So this is what we've been talking about. So we establish this rejection region. If our z-score is in that region, we reject. If it's not, then we fail to reject. So again, here's what the pictures look like for that as well. And so let's run through the steps again that we're going to use for rejection region hypothesis test. Again, we want to do our central limit theorem, make sure that applies. State our null and alternative, that's the same. Find our alpha, that's the same. Determine our critical values. Again, for this, we're going to use inverse norm. Determine the rejection region, that's our RR. Find our test statistic, that's the same. Again, we're going to use parentheses to do that. Then we're going to make our decision to reject or fail to reject based where the z-score is at. If it's in the rejection region, we're rejecting the null. If it's not in the rejection region, we're going to fail to reject the null. We're going to interpret the decision based on the original claim, just like we did previously. So here we go. Let's run one of these. So we are doing a hypothesis test with a rejection region. We're going to do, I think, 3 of these examples. Yep. Employees at a construction and mining company claim that the mean salary of the company's mechanical engineers is less than that of one of its competitors, which is $68,000. A random sample of 20 of the company's mechanical engineers has a mean salary of $66,900. Assume the population standard deviation is 5,500, and the population is normally distributed at alpha equals 0.05. Test the employee's claim. Well, what are they claiming? They're claiming that the mean salary is less than $68,000. So the mean is less than 68,000. There is no equal, so that's the alternative hypothesis. Therefore, the null is the opposite, which is the mean is greater than or equal to $68,000. Because this is the alternative, which going to the left, this is a left-tailed test. So we can sketch a picture here. Here we actually need our alpha. Our alpha is 0.05 because it's a left-tailed test. Then 0.05 is here. And so our Z naught score is inverse norm of 0.05. We're going to plug that into our calculator, and that is a negative 1.64. And that's going to the left. Therefore, our rejection region is negative infinity negative infinity to negative 1.64. So now we're going to calculate our test statistic, Z. If Z is inside this, we reject. If it's not inside this, then we fail to reject. Well, to calculate that, it's the same thing we've been doing. X bar minus mu over sigma divided by square root of n. Again, use parentheses on that. So this is 66,900 minus 68,000 divided by 5,500 divided by square root of 20. Therefore, our z-score is negative 0.89. So here's the question. Is negative 0.89 smaller than negative 1.64? It's not, it's bigger. Remember, these are negative numbers, so those rules work. The smaller number is actually the bigger number. And so it is not in the rejection region, so we fail to reject. Therefore, there's not enough evidence to support the claim. So there's one, we're going to do two more. The CEO of the company, example 9, claims the mean work day of the company's mechanical engineers is less than 8.5 hours. A random sample of 25 of the company's mechanical engineers has a mean work day of 8.2 hours. Assume the population standard deviation is 0.5 hours, half an hour, and the population is normally distributed. There's our central limit theorem, and alpha equals 0.01. Test the company's claim. So again, just like with our p-value test, we want to write the claim. This works the same. So what are they claiming? Well, their claim is that their workday, their average workday is less than 8.5 hours. There's no equal. So our claim is the alternative hypothesis. Therefore, the null is the opposite, which is greater than or equal to 8.5. Because this is less than, this has to be a left-tailed test. And we know our alpha is 0.01. So here's our left-tailed test. We need our z-naught score for a 0.01. That is inverse norm of 0.01. And that is negative 2.33. So here's our negative 2.33. Because this is a left-tailed test, we're going to the left. To the left of this then for our rejection region is negative infinity to negative 2.33. Now we want to calculate our test statistic and see if it's inside that rejection region. If so, reject. If not, we fail to reject. Again, our z-score is x bar minus the mean over sigma divided by square root of n. We're going to get all of those numbers from the problem. The claim is always the mean. So we're subtracting from 8.5. Our sample gave us an 8.2 over the standard deviation of 0.5 divided by the square root of 25. Again, parentheses and all that. Our z-score test statistic is negative 3. Does negative 3 fit inside our rejection region? Yes, it does. Negative 2 is smaller than negative 2.33. Therefore, yes, it's in our rejection region. Therefore, we're going to reject the null hypothesis. Because our claim is the alternative, we're going to use the word support. So there is enough evidence to support the claim that the average workday is less than 8.5 hours. And last one, this was a long video. This is a long lesson. The researcher claims that the mean cost of raising a child from birth to age 2 by husband and wife families in the US is $13,960. A random sample of 500 children. Age 2 has a mean cost of $13,725. Assume the population standard deviation is 2,345. And alpha equals 0.10. Is there enough evidence to reject the claim? So what is the claim? The claim is that the average cost to raise a child is, it's not bigger, it's not smaller, so it's equals 13,960. That's got to be the null. The alternative then is the opposite, which it is not equal to 13,960. 960. Therefore, we have a two-tailed test. Because we have a two-tailed test, and we have to split alpha in half. Our alpha is 0.10. We're going to divide that in two. So here's 0.05 and 0.05. So our Z naught is our inverse norm of 0.05. We'll plug that into our calculator. We'll get negative 1.64. The opposite has to be true as well. 1.64, you can find that by inverse norm of 0.95. Therefore, our rejection region is negative infinity to negative 1.64 union 1.64 to positive infinity. Now we need to find our test statistic, Z-score, is the sample cost, 13,725, minus the average cost, 13,960, divided by the standard deviation, 2345, divided by the square root of 500. Again, parentheses around all that. Our Z-score then is negative 2.24. Does that fit in one of our rejection regions? Yes, it does, because it is smaller than negative 1.64. So we're going to reject the null. Because our claim was the null hypothesis, we're going to use the word reject or fail to reject. Here we rejected the null. So there is enough evidence to reject the claim. And the claim was that the mean cost of raising a child is 13,960. All right, so there's our second method of hypothesis testing, and that was using a rejection region. I'm going to skip this last one. So we talked about doing finding the p-value. We talked about doing a z-test for finding the p-value to run our hypothesis test. We also talked about finding critical values in the rejection region to do a hypothesis test with a rejection region. You will have both on the last test. And your homework then is 2 through 42 evens. Only 21 problems, but they're kind of involved problems. Message me, email me if you have questions. Good luck working through that one. 3 more to go. Have a good day, Maroons.